Hello, everyone. My name is Owoyele from Argonne National Lab. Today, I'll be talking about a mixture of experts-based learning of combustion manifolds. So my motivation for this study first, numerical simulation of turbulent combustion is computationally intensive, especially when you're including detailed chemical kinetics. And that's because usually that means that you'll have to transport a large number of species in space and time. Physical reduced order models, such as the Flamelet model, has emerged as a promising way to solve this problem. And here, essentially, the evolution of a chemical species is assumed to be described by Z, which is a mixture fraction if you have a diffusion flame, and other control variables. Oftentimes, you can further accelerate simulations by solving the relevant equations a priori and simply storing the solutions in a lookup table. The problem with lookup tables is that the table size increases exponentially as the dimensionality, which in this case, the number of control variables, as that increases. Usually this prevents, its application to many practical problems where we need a lot of control variables to properly capture physical behavior. The way this is typically done in practice is that you run sort of like a low-cost simulation, so a counter-fluid diffusion flame, like I said, and you generate a table from that. And when you generate a table, the table will contain your control variables and the corresponding mass fractions. And typically what has been done is you can take that table and you can import it to your CFD solver. So you have to store the table in memory. And then you look up the table during simulations to retrieve mass fractions. The problem is that this is intractable, like I said, if you have high dimensional tables. And so what we can do instead is that we can learn the table using deep neural networks. And once we have that, the neural network would learn to predict the mass fraction as a function of the control variables. And once we have that, we can then import that to the CFD solver. And the good news is that if we have a neural network, we only have to store the model parameters and architecture, as opposed to trying to store the entire lookup table in memory. The problem with neural networks, the drawback, is that if the relationships between input and output is complex, then typically you would require a large neural network that's hard to train. And usually several parameters would be required, and which means that when you stick it in your CFD solver, it's going to slow everything down. And so even though neural networks are quite helpful in terms of saving memory, they have their own challenges. So the way we solve this problem in this study is by using a mixture of experts approach, which I'll refer to as MOE moving forward. The MOE structure is shown here. So it has, as opposed to one neural network, it has multiple regression models, and they compete for input signals during training. So they compete for each sample. And the gating network acts as sort of a supervisor of this problem, and it feeds regression models that perform well. It feeds them with even stronger training signals in future. These regression models I'll refer to as experts moving forward. And the complex manifold is sort of bifurcated into simpler manifolds. And then you have a small network that will be fit for each bifurcation. And so the gating network tells you, which of these models apply for each sample. One way to visualize it is to sort of look at this simple problem here. So this is sort of like a piecewise linear function. And if you apply MOE to this problem, you get something like this, where it's sort of split up at the points of discontinuity in X. And what the MOE approach that we are going to show in coming slides, it achieves this same thing, except that here we're dealing with nonlinear problems in high dimensional input spaces. In terms of the training of the MOE, this is what it looks like. So this is the loss function. As you can see, the loss function doesn't just depend on the expert K you're interested in, it also depends on other experts. The sort of big takeaway from this slide is that we could differentiate the loss function with respect to the neural network parameters. And what that would actually do is The learning rate for each expert would be weighted by this term here, alpha sub k. Essentially what this term does is that if EK, which is the error of a given expert, is large, then this term is going to tend to 0. And so the learning rate for that sample where that expert has a large error would be sort of slowed down. The learning will be slowed down. And the opposite is true. If the error is small compared to the other experts, then it's going to be made to learn faster and others would be made to learn slow. That's the basic idea. This right here is a problem setup. And so in this case, the MOA was validated in context of unsteady Flamelet progress variable model, UFPV for short. And here we have for control variables. So we have Z, which is a mixture fraction, the variance of mixture fraction, chi, which is the scalar dissipation rate, and C, which is a progress variable. The 4D manifold is generated by solving the Flamelet equation a priori. And the solution was based on an unsteady end-decaying counterflow diffusion flame. The pressure was at 60 bar, oxidizer pressure was at 900 Kelvin. The chemical mechanism size, it contained almost 3,000 species. So these are some of the a priori results. So in these cases, we are not actually running simulations. The goal is just to train and then plot and see how we're able to reproduce what we get from the table. So on the left here, we have YCO2 versus Z, the mixture fraction for different values of C, which is the progress variable. The lines in the plot, the solid lines are the Flamelet table. The lines with the circular symbols are MOA. The X symbols represent a global ANN model, a single ANN, SANN for short. And what we see on the left here is that MOA produces much better results. It agrees pretty well with the Flamelet table. Meanwhile, using a global neural network introduces significant errors. We see the same thing on the right. It's looking at it from a different angle. So here, it's the mass fraction of CO2 versus the progress variable for different levels of mixture fraction. ZSC here is simply the stoichiometric mixture fraction. And we see the same thing using a global ANN model introduces significant errors, while the accuracy is improved significantly when we use specialized models that MOA provides. We have results on the left here for OH. So this is the mass fraction of OH against Z, and this is the mass fraction of formaldehyde versus the mixture fraction. And here again, it's quite evident that we see the same trends. Trying to use a global model doesn't work quite as well as using specialized models that we get from MOA. Here I'm showing some of the training errors in a sort of more compact fashion. So we have the mean squared error against for different as a function of the number of experts that we use, and we're showing this for different neural network sizes. So in this case, 12 by 4 network simply means we have 12 neurons and we have 4 hidden layers, right? And so what we see here is that there are 2 ways to reduce training errors. One way is to use more experts. The second option is to simply use a larger network. However, what we see is that we can use a much smaller network of 4 by 4 with 8 experts and get the same errors as we get by using a much larger neural network that's 12 by 4 if we want to use a global model. So what this translates to is that inference speeds are about twice as fast compared to a global model. We see the same thing also for OH as well. We see the same trends, and compared to the table, we can also try using GPU-based machine learning inference to further speed up inference speeds too. So we also had results for a 5D table where we had 9 pressure levels added to the 4D table. So in this case, we had 50 million entries, which we introduced storage issues on some compute clusters. In contrast, as opposed to 14 gigabytes for the table, storing the table in memory, the global ANN and MOE approach only required 508 kilobytes and 3.4 megabytes, respectively. So these are showing similar plots to what I showed again, to what I showed some slides earlier. This is why H versus Z. We see again that, using the single ANN is not very accurate. Using the specialized models give much better results. And again, this is just showing that using net experts, we can get errors that are even that are much better than using one expert or a global model. We also extended this to an a posteriori validation approach. So here we actually coupled MOE with a CFD solver. The setup here is an ACN spray A. So you have spray coming in, it breaks up, it evaporates and mixes with the ambient air. And then you have ignition and you have a flame forming. The code we use here was Converge, which is a 3D code with adaptive mesh refinement. The pixel count in this case was 450,000 in the domain. The turbulence model here was RAND's RNG Epsilon model. The ambient gas temperature was 900 Kelvin. So the workflow is sort of illustrated here. So this part is done offline, and this is where we actually solve the Flamelet equations a priori. And once we solve the Flamelet equations a priori, we get the mass fractions as a function of the control variables. And once we have that, we can import that to our CFD solver where we solve for continuous momentum and all the conservation equations. From that, we can get the control variables, and we can then use that to retrieve the mass fractions from the table, and then retrieve temperature and so on. What we're doing here is that we're replacing this with a neural network. And so instead of a table here, now we have a neural network that's taking the control variables and giving us the mass fractions. If we have other physical phenomena, we would need to add other control variables such as pressure and enthalpy to this problem, and that's where the table size would really grow. So these are some of the control plots that we get at 0.9 milliseconds after injection. So this is showing temperature at the top, H2O in the middle, and OH at the bottom. And we're comparing MOE on the left and UFPV, which is the table, showing the table in memory on the right. And what we see is that we get good agreements for temperature. For instance, the predictions, the peaks seem to be a little bit lower for temperature, but the trends are captured well. For H2O, we get good agreements. It looks almost exactly the same. For OH, we see some discrepancies, mostly in terms of how broad the zone of peak OH concentrations are. But in terms of the regions where those peaks do occur, we get good agreements in that sense. Here we have some more global quantities. So we have the ignition delay for experiment, interpolation, and MOE. Interpolation here is the table. And so we have 0.44 compared to 0.46 and 0.459. So what we see is that the MOE accurately captures the ignition delay. The ground truth in this case would be the interpolation because we trained the MOE based on the table. In terms of memory savings, the table size is about 1.4 gigabytes. On the other hand, the MOE size is about 1.2 megabytes. So we get about 100x speed up, 100x memory savings. The maximum temperature is shown here. Here we see that MOE accurately captures that. We have an initial zone here where nothing's going on. We have sort of like a first stage of rapid temperature rise. It sort of slows down, and then a second stage before it flattens out, and that's accurately captured by MOE. The heat release rate is also shown. There is a slight over-prediction around when ignition occurs. However, the trends are in general accurately captured. So here's my summary slide. So in this work, I've presented a mixture of experts framework that involves training multiple neural network experts to first bifurcate and then tabulate multi-dimensional combustion manifolds. And we showed an a priori validation with 40 and 5D Flamelet table. We also showed an a posteriori validation for ACN spray A. And ongoing work we're working on at the moment is to also include the progress variable source term in the a posteriori analysis. So that's something that we're not doing at the moment. And in future, we also hope to use MOE for higher dimensional tables where we have even more memory issues, and also explore in-situ training and also GPU-based machine learning inference to even speed it up further. Here's my acknowledgement. So this work was funded by the US DOE. So we'd like to appreciate our program managers, Gurpreet Singh and Michael Wise-Mailer, and also computing resources from Argonne's LCRC clusters. With that, I'll end my presentation and I'll be happy to take any questions. Thank you for listening.